in order to talk about the other three trigonometric functions, cosecant, secant, and cotangent, we need to remember that they are reciprocals of sine, cosine, and tangent respectively. And that means we need to talk about reciprocals and how they actually work. There are certain relationships that reciprocals have with each other that are going to help us define these other three functions. So, a few things. One thing that we already know from dealing with the basic rational function y equals 1 over x is that the larger a value is, the smaller its reciprocal will be. And vice versa, because these values are reciprocals of each other. So for example, 100 has a reciprocal of 1 over 100. One million has a reciprocal of 1 over 1 million. Now, if, in case it's not clear there, the decimal forms of these are as follows. You can see that the larger the original value, the smaller its reciprocal is. The larger, as it gets even bigger, its reciprocal gets even smaller. But this relationship is bidirectional. It's not just that the bigger the number I start with gets, the smaller its reciprocal. It works the other way too. The smaller the reciprocal gets, the bigger the original value is. So that's something to keep in mind, that the bigger one thing gets, the smaller its reciprocal gets, or the smaller something gets, the bigger its reciprocal gets. Now, that's one thing to keep in mind. The other important part of this is that any value smaller than 1, its reciprocal will be bigger than 1. Oh, excuse me. If any value is smaller than 1, then its reciprocal is bigger than 1. Look at it this way. If something is smaller than 1, then its value is a fraction. And fractions tend to either be proper or improper. A proper fraction is when the numerator is smaller than the denominator, such as 3/5. However, an improper fraction is exactly the opposite. The idea then is that in a proper fraction, if the top is smaller than the bottom, as soon as we switch them, well, if the bigger number had been in the bottom and they now switch, the bigger number is now in the top. So if we have a small number in the top and a big in the bottom and we switch them, we get an improper fraction. So that's something else to keep in mind. It's particularly relevant because all of the output values of sine and cosine are smaller than or equal to 1. And that means that the output values of the reciprocals will always be bigger than 1. So let's take a look at cosecant of x here for a moment. And let's remember that cosecant is the reciprocal of sine. Now sine, let's remember, has a domain of all real numbers, and it has a range from -1 to +1. And it has its 5-point summary, which we'll get to in a moment. But here's the important thing, is looking at the output values of sine of x. If the output values of sine of x are all smaller than, or perhaps equal to, 1 or -1, then their reciprocals all have to be bigger than 1, or bigger than -1, just with a negative sign. So that tells us something about the range of cosecant x. For cosecant of x, we can have output values that are negative but bigger in magnitude than 1, or bigger than +1. Any positive output for sine, 0 to 1, is going to result in a large positive reciprocal from anything from 1 to infinity. And the same thing on the negative side. So that's interesting. Now, as for the domain of cosecant of x, we need to be careful. Sine of x is defined for all real numbers, but at some of those places, sine of x is equal to 0. So we need to keep something in mind here, that there are points like sine of 0 is equal to 0, or sine of pi is equal to 0, etc. And the thing is that at each of these places, if sine is 0, the reciprocal is therefore undefined. So, while sine has a domain of all real numbers, there are output values in the sine function that are 0. And whenever that happens, cosecant is going to be undefined. So as it turns out, the domain of cosecant of x is going to be, well, actually somewhat reminiscent of the domain for tangent function. There are going to be periodically places where the cosecant function is undefined. In this case, it's going to be at whole number multiples of pi. So x cannot be any integer multiple of pi. Now, all of the other characteristics of cosecant of x are the same as sine of x. That is to say, they have the same period. Now, cosecant is not going to be a wave, but it is going to have an amplitude after a fashion. Much like tangent did, it will be affected by a vertical distortion, and it doesn't have a midline in the sense that sine does, like a wave. But the kind of entire idea of cosecant of x is that it's entirely based off of what the sine function is doing. So let's come down here and take a look at the sine function, and will help us understand what cosecant is doing. So, the sine function, as we well know, The sine function, as we well know, goes through 0, 0, and then it goes through pi over 2 comma 1, and then back to its midline, and then 3 pi over 2 comma negative 1, and then back to its midline. And it repeats this pattern forever. And in the other direction as well. And we get this nice waveform. And this is the sine function. This is not cosecant yet. We get this nice waveform of the sine function. Now, we can use the 5-point summary of sine of x to help understand what goes on with cosecant of x, starting with what we already said about the domain. Anytime sine of x is equal to 0, cosecant is going to have an asymptote because it is undefined there. So sine of 0 is 0, sine of pi is 0, sine of 2 pi is 0. And anywhere else that the sine wave touches the x-axis, cosecant of x is going to have a vertical asymptote. Now, in between, it's just a matter of tracing what sine of x does. The idea is, of course, that the smaller the value of sine, the bigger the value of cosecant will be, because they are reciprocals of each other. So sine is at its smallest, but positive, right there. Right just past 0. Sine is at its smallest positive value, which means its reciprocal, cosecant, is going to be at its largest positive value. And then the sine function is going to increase until it hits a y value of positive 1. But as sine gets bigger, cosecant is going to have to get smaller until it hits 1. Because the reciprocal of 1 is 1. After this point, the sine wave drops away from that point, and as it drops away, cosecant is going to rise up. The same behavior will happen every time sine bows up above the x-axis. And the same thing will happen below the x-axis, because the only difference is that all the values are negative. So as sine dips below the x-axis, cosecant will come up to meet it and then drop away again. So actually, the best way to draw a cosecant function is to first draw the sine function and then draw the cosecant function to match it. That actually is the entire key there, is that if whatever transformations are happening to sine, just graph that sine function with all of its transformations, and then do this to get cosecant, And when all is said and done, that's what your cosecant graph looks like. Vertical asymptotes, and in between, almost a parabolic shape, really. Secant is going to have very much the same relationship with cosine. Secant of x is the reciprocal, is the reciprocal of cosine of x. So, once again, we can look at the characteristics of cosine of x, which has the same domain and same range as sine of x, and therefore its reciprocal, secant of x, is going to have some very similar things as well, including the range, where it can be everything below -1 or everything above +1, because it is the reciprocal of cosine, which is always between -1 and +1. Now, cosine, like sine, has values where it's equal to 0, but they are different values. Cosine is equal to 0 at pi/2 and 3 pi/2. Actually, much like tangent. These are actually all the same locations that tangent is undefined. And whenever cosine is 0, its reciprocal, secant, will be undefined. And once again, the graph of this is going to be done with the cosine function first. And from that, we can draw the secant function. So cosine differs from sine in that it starts at its high point and then proceeds to its midline, then down below, and back up, and so on. And again, the same thing in the other direction. So once again, wherever the cosine wave hits the x-axis, wherever cosine is 0, we're going to get an asymptote, because those are the places where secant is undefined. Note that these are not exactly in the same places they were for cosecant. In between, we get very much the same behavior that we had for cosecant. Whenever the cosine wave dips below the x-axis, secant is going to rise up to meet it, and then fall away again. And whenever cosine rises above the x-axis, secant will drop down to meet it, and then go back up. So much as sine and cosine have very much the same graph, just slightly offset from each other, secant and cosecant have very much the same graph, just again, slightly offset from each other. And once again, the way to graph this is going to be to graph the cosine function with any of its transformations, and then from there draw in the secant, the parabolic style shapes of the secant function. That just leaves us with cotangent. Cotangent is the reciprocal of tangent. Now, tangent was different from sine and cosine because tangent had certain had asymptotes built into its domain. The domain for tangent was that x could not be pi over 2 or any number of half rotations of the circle away from it. However, the range of tangent was all real numbers. Now, that includes, again, every number in existence, which means if every number's out there, their reciprocals are also out there, and that's everything. So once again, what we're going to see for cotangent here is that the reciprocal of literally any value out there is going to give us, again, any value out there. But, like sine and cosine, the range of tangent includes 0. There are angles where the tangent value is 0. So those angles are not going to be included in the domain of cotangent. However, interestingly enough, the places where tangent is undefined, that's where cotangent's going to actually be equal to 0. So they have that reciprocal relationship. If the reciprocal of 0 is undefined, then the reciprocal of undefined, if you will, is going to be equal to 0. So where one of these is undefined, the other is 0, and vice versa. So tangent is 0 at 0 pi and 2 pi, which means that's where cotangent is undefined. But cotangent is 0 at exactly the places that tangent is undefined. So that's an interesting little thing to note there. That cotangent is 0 when tangent's undefined, and tangent is 0 when cotangent's undefined. Now, like the sine, or like sine, cosine, and cosecant and secant, it helps to look at the graph of tangent to understand what's going on with cotangent. Although this time they're definitely going to overlap a bit. So I'm going to draw in tangent without its asymptotes because it's just going to be much easier to distinguish one function from the other. But tangent goes through negative pi over 4, negative 1, 0, 0, and pi over 4, comma, positive 1, and it approaches its asymptotes at negative pi over 2 and positive pi over 2. And then it repeats that in the next interval, and so on and so forth. Okay, so that's what tangent does. Now, as we said, wherever tangent is 0, that's where cotangent is going to have its asymptotes. And wherever tangent has its asymptotes, that's where cotangent is going to be 0. So when one is 0, the other has an asymptote, and vice versa. Now, in between, much like with sine and cosecant, or with cosine and secant, when one graph is at its smallest, the other is at its biggest. So right past its central point there, tangent is just barely above 0. Positive, but very, very small, which means cotangent is positive and very, very large. And as tangent rises up to 1, cotangent has to come down to 1. But from there, tangent extends upward forever, which means cotangent has to come down towards 0. On the other side, we have tangent being as largely negative as you can imagine, which means cotangent is very slightly negative. But as tangent comes up towards -1, cotangent has to drop towards -1. Excuse me. And then as tangent continues up towards 0, cotangent has to observe its asymptote. So what we get here is actually a very similar style, a very similar style function, except instead of going up and to the right like a cubic function would, cotangent comes down and to the right. It actually goes through a lot of the same points. But it does it coming downward instead of going upward. So again, a very particular relationship between cotangent and tangent because of the fact that they are reciprocal functions. But in essence, the key to understanding cosecant and secant and cotangent is to understand what's going on with the original three and then apply the reciprocal concepts to it. So in that way, you don't actually end up with 6 different sets of functions to remember and deal with. Really, you just need to know sine and cosine and tangent, and you need to understand the concept of reciprocal to build the other 3. As it turns out, you don't deal with the other 3 nearly as often. They're not nearly as commonly occurring as sine and cosine and tangent, at least not until much higher levels of math. But just to get this out there and see what they look like and understand how they work and how they come about from from understanding the relationship between reciprocal values. So if you understand sine and cosine and tangent, then you can get the cosecant, secant, and cotangent graphs from them using reciprocal concepts.